Okay, this example is showing how to calculate pH of a buffer solution. Okay, so this buffer contain 0.1 molar weak base and 0.2 molar ammonium chloride. And given the Kb for weak base ammonia is 1.8 times 10 negative 5. So to solve this question, we have to use Henderson-Hasselbalch formula, which is pH equivalent to pKa plus log of concentration of base divided with concentration of acid. So first of all, we have to find pKa. And how to find pKa from Ka? So how to find Ka using Kw, Ka and Kb expression, in which Kw equivalent to Ka multiply Kb. So to find Ka, Kw divide with Kb. So you are given Kb here, you have to memorize Kw, so you can calculate Ka. So negative this Ka, okay, negative log Ka, you get pKa. Okay, so this 9.25 you substitute in the Henderson-Hasselbalch formula. Okay, and then for concentration of base over acid, okay, acid will be the denominator here, okay, because we are calculating pH. So pH here, so at the bottom should be acid. Okay, so divide first, okay, concentration of base over acid, then you log. After that, then you add 9.25. You should get at 0.95. Okay, so this buffer solution is basic because it's made of weak base. Okay. Now, this example is different from the previous example because the buffer is prepared. Okay, you are preparing the buffer. The previous example, the buffer already prepared, and the final buffer have concentration the final concentration of the acid is 0.02 and base is 0.01. But here the concentration is before the mixing. Okay, so here the buffer is being prepared by mixing 45 ml of 0.15 molar sodium fluoride to 35 ml of 0.1 molar hydrofluoric acid. So here the buffer is being prepared using weak acid and its conjugate base. So given Ka for hydrofluoric acid 6.8 times 10 power negative 4. So how to solve this question? Remember, you are mixing. When you mix, the concentration is no longer 0.15 molar for sodium fluoride and it's no longer 0.1 molar for hydrofluoric acid. So we have to find the final concentration first before you substitute it in the Henderson-Hasselbalch equation. So we use Henderson-Hasselbalch formula to solve that question just now, but what we need to do first is calculate the new concentration of both the weak acid and conjugate base after the mixing. Okay, and how do we do that? We use M1V1, M2V2 formula. Okay, M1V1, M2V2. Okay, this is for acid. Okay, M1V1. Please excuse the messy writing because I'm just using my mouse here. So this would be for the conjugate base. Okay, so what is the original volume of the acid? 35 ml. Okay, 35 ml of hydrofluoric acid. Okay, what is the concentration of the hydrofluoric acid? 0.1 molar. Okay, So after mixing, what is the final volume? Okay, this we want to find out what is the new concentration of this acid. After mixing, what happened to volume? Of course, 35 plus 45 of the volume of the base, so it become 80. Okay, note that I'm using mil here. Okay, you can use mil if both side you use mil. You can convert this to liter, but this side also have to be converted to liter. Okay, so the new concentration of acid would be M2 would be 0.044 here. Okay, 0.044. So conjugate base, okay, the original concentration would be 0.15. The volume is 45. Okay, and we want to find the new concentration. Again, volume would be the same because you mix, so 80. So M2 for the conjugate base would be 0.08. Okay, here. Okay, so then you substitute the acid. The base here, the acid here, and then Ka is given, so you just negative log Ka to get pKa. So the pH would be 3.43. Now how to solve this question? Okay, the first part will be easy because we have covered it in the previous example. Okay, the new one would be this. Okay, now first of all, what is the pH of a buffer solution that is 0.2 molar ammonia and 0.3 molar ammonium? Okay, so the buffer is being prepared using weak base and conjugate acid. Alright, to solve question I, okay, we use Anderson-Hasselbalch equation. Okay, so the buffer was already prepared, so you just substitute the concentration of the conjugate acid inside and also base ammonia. Okay, and then you are given the Kb, you just negative log to get Kb, pKb. Okay, so in this case we will calculate pOH because it's a weak base. So when you use Anderson-Hasselbalch, if you use pH, then you use pKa. If you use pOH, then you use pKb. And here will be the other way around, following what is at the front here. So if you are calculating pOH, then the denominator will be base. Okay, if you're calculating pH, then the denominator will be acid. So substitute the concentration of both conjugate acid and base. Okay, we should get pOH 4.92. Okay, so to find pH, we minus from 14. So this would be the concentration of the buffer. Okay, not it was made from weak base, so the pH will lies in the basic region. Now how to solve question part 2. Okay, so remember the buffer was added with strong acid, okay, hydrochloric acid. So means what happened to this concentration here? It will change. Go back to the figure that I have shown you in previous link, in which when you add acid or base, okay, you will use up the same amount of the buffer to counter the addition of strong acid or strong base. Okay, so this is what we should do. Okay, so when we add acid, which one will counter the addition of acid? Of course, base. So this one will reduce, and this one will increase in same amount as this reduced. Okay, so if we have 4 of this present, 1 is added in, so it becomes 3. Okay, so this original also 4, then it becomes 5. Okay, so that is the how we imagine. Okay, so that is considered as number of mole. Okay, so number of mole. So number of mole of ammonia react with the hydrochloric acid will be equivalent to number of mole hydrochloric acid. Okay, so how to find the new concentration of ammonia? Remember, this one reduced just now, so minus. Okay, number of mole initially present minus number of mole react with the acid, and then you divide with total volume to find the new concentration. Okay, so initially present, you have 400 ml of buffer and 0.2 concentration of ammonia, minus 100 ml of hydrochloric acid, strong acid, at 0.005 molar concentration. So minus over the new volume. Okay, 400 of the buffer plus 100 of the strong acid becomes 500. So this would be the new concentration of ammonia. How to find the new concentration of conjugate acid, ammonium chloride? Okay, so this one reduce, forming this, so this one should be increase. So here number of mole present plus, so you correct this. Okay, so that one should be plus. Okay, plus number of mole that react with hydrochloric acid. Okay, over total volume. So 400 volume of buffer times concentration of conjugate acid plus 100 ml of 0.05 molar strong acid over the total volume 500. So this would be the new concentration for conjugate acid. Then you substitute into the Henderson-Hasselbalch formula, because this buffer was made from weak base, so we use POH and pKb. Then we minus from 14 to get pH. Okay, next example should be easy because the buffer is already prepared, and Ka for the weak acid, chloroacetic acid, was given here, 1.4 times 10 power negative 3. Okay, so you just substitute the concentration of base over acid, then you log plus negative log of the Ka value of chloroacetic acid. Okay, so you get pH here. Now, example 12. How many mole of sodium acetate must be added to 2 liter of 0.1 molar acetic acid to give solution that has pH equal to 5? Okay, and then ignore the volume change due to the addition of sodium acetate. So the answer is given here, so I want you to try work this out first on your own. Okay, see whether you get the answer here, 0.34 mole. Okay, so moving on next, okay, is polyprotic acid. Poly, so poly means more than one. Okay, so when it's more than one, means it has more than one ionizable proton. Okay, however, the removal of the proton cannot be done at once. Okay, you have to remove one by one. Okay, so of course it's easier to remove the first proton compared to the second, the third, and so on. Okay, and that's why you see the Ka value will be so much different. Okay, after the okay, so you see here, you have H2SO3. Okay, sulfurous acid. So the removal of the first proton will be easier. That's why the Ka value is 1.7 times 10 negative 2. But then removal of the second proton, this one, okay, will be, the Ka will be 6.4 times 10 negative 8. So you see very much different. Okay, so Ka1 will always bigger than Ka2. Ka2 will always bigger in value compared to Ka3. Okay. Okay, the final part is acid-base property of salt solution. Now, I'm sure you are very familiar with salt, but how do we know that particular salt is acidic or basic? Okay, so first of all, almost all salt are strong electrolyte. Strong electrolyte means it ionized completely, okay, in solution. Okay, for example, table salt that you have at home, garam in ACL. Okay, when you put salt inside water, it will completely ionize to sodium ion as well as chloride ion. Okay, no longer sodium chloride present. Okay, because they are strong electrolyte. Okay, so how to find the property of this salt? Is it neutral? Is it acidic? Or is it base? Okay, so there are rules to that. Okay, so note here, anion from weak acid are basic, anion from strong acid are neutral. Okay, for example, you have HNO3. Okay, HNO3. Okay, so it will ionize to give you H plus and NO3 minus. Okay, anion from weak acid are basic. Example, let's say acetic acid, CH3 COOH. So it ionized to give you CH3 COO minus plus H plus. Okay, so this anion here, CH3 COO minus, are basic. Okay, anion from strong acid here, NO3 minus, neutral. Okay, so first of all, get the anion, okay, plus add you write it plus with H2O and see what is the product. Okay, that's how we identify whether that particular salt is base, acid, or neutral. Okay, in property. Okay, so next is cation, ability to react with water. Okay, so this is cation, okay, NH4 plus. Okay, you add with H2O, you get NH3, NH3O plus. So some metal ion react in solution to lower pH. Okay. Combined effect of cation and anion. Okay. Anion from a strong acid has no acid base property, and anion from conjugate base of a weak acid will leads to increase in pH. Okay. Cation, that is the conjugate acid of a weak base, will cause decrease in pH. Okay, decrease in pH. Metal ion will cause decrease in pH. Okay, metal ion, except the alkali metal and alkaline earth metal group. Okay, except group 1 of predictable and group 2. Okay, and if a solution contain both cation and anion from weak acid and base, we use Ka and Kb to determine the final pH of solution. Now, I'm sure you cannot digest this, okay, by listening to my explanation. Okay, to understand this better, let me give you an example. Okay, now let's say I give you BA, CH3, COO2. Okay, so this is a salt. Now you tell me, what is the characteristic of this salt? Is it base, is it acid, or is it neutral? Now, first of all, when you are given salt like this, you write the dissociation, okay, of the salt. So it will dissociate into barium 2+, and CH3, COO minus. Okay. Now, first we look at the anion CH3COO. Okay, remember anion you add with H2O. Okay, CH3COO minus. So you add with H2O. So H2O is comprises of H plus as well as OH minus. So which one will react with the CH3COO minus here? Of course, H plus. So you get CH3COOH. Now, this CH3COOH, what type of acid is this? It's a weak acid. Okay, so remember the rule, anion from weak acid are basic. Okay, so this would be basic, CH3COOH. Okay, so this will be basic. Okay, so this will be basic. Now, how about Ba2+? Okay, go back to the statement. Metal ion will cause a decrease in pH except for alkali metal and alkaline earth metal. So barium belongs to alkaline earth metal group 2. So therefore, it will not cause a decrease in pH. So it is neutral. So therefore, this salt is therefore basic. let me give you one more example. Okay, NH4Cl. NH4Cl. Now what we must do first step, write the dissociation of this salt. So it become NH4 plus Cl minus. Now that Cl minus here, we add with H2O, so it become HCl. HCl is what? Is one of the strong acid. So because it's one of the strong acid, it is neutral. So anion from strong acid are neutral. Okay, one of the rule. So therefore this one neutral. Now go back and now let us look at the cation NH4 plus. Okay, so NH4 plus, we add with H2O and we get NH3 plus H3O plus. Okay, the previous example. So H3O plus will lead to decrease, lower in pH. Okay, lower in pH. So it will become acidic because lower in pH. Go to the previous slide, okay, with the example of NH4 plus add H2O. So therefore this salt would be acidic. Okay, now this example 13, okay, calculate pH of 0.1 molar ammonium chloride solution. Kb of ammonia is this. So first we find Ka. Okay, find Ka using Kw divided with Kb, so we get Ka here. Okay, so based on the expression of Ka, okay, which is product of a reactant, we can solve X. Okay, X will refer to H3O plus here, so meaning that you negative log of this H3O plus concentration, you get pH. Okay, and example 14, calculate pH of 0.3 molar sodium chloride. Okay, the Ka value is given, okay, for the weak acid, okay, HF. So use the Ka to find Kb, because you need to calculate pH of the conjugate base. Okay, so Kb, so we find Kb here. Okay, put it in the expression of product of a reactant. Okay, concentration of conjugate base is 0.3. Yeah. Okay, so this is Kb, so we get X. So X will refer to OH because it's base, conjugate base. So we refer to OH. So to find pH, minus from 14. Okay, so that is example 4.